What are we looking at here?
Do you wanna say?
It looks like a ghostly image of Mauna Kea. I think I can maybe see one of the cat domes here.
Yeah,
Yep.
in the corner, yes.
Right
So
here.
yeah, weather's not good today. It's very foggy. The dome's closed, so we can't actually do any observing today.
Yeah.
But
So despite the fact that it's like not actually raining, fog has like droplets of water, and this humidity is really bad for the instruments that are in the telescope. So we don't want that water, that precipitation to get into the electronics. So that's why we have to close when it's this foggy. Despite, in the background, you can see some stars, but we cannot observe them with the telescope. Yeah.
Ah, yes, okay, because I definitely know what it's like with one of my small telescopes, or even just when you leave binoculars or anything outside, that condensation just gets everywhere. And certainly for such an incredible piece of machinery as the Keck telescopes, you don't want water anywhere near anything.
Yeah.
Uh, so that's well, we're excited to be here with you though, just to learn more about your research. And maybe, just maybe, while we're together, you'll get the signal that it's okay to open. So we'll keep our fingers crossed as you share some background with us about the work that you're both doing.
Yes.
sounds good.
I like the optimism. Oh, next computer. Um, okay, so we're going to show you a little bit of the science that we are aiming to do. And for that, we have written a presentation. Um, so our presentation is called Breaking Math, where we observe gravitationally lensed galaxies with the Keck telescopes. And this research is mainly supported, or like all the science is going to be done by William and another PhD student called Sean Nabel. And I'm a postdoctoral researcher, so I already have a PhD, and I'm in the team of looking for gravitational lens galaxies of the University of California, Los Angeles. And I don't work directly on gravitational lensing. I work more on like galaxies that are very, very far away and supermassive black holes. But I like to come and observe at Keck because, as we were saying, Keck is just amazing. It's a 10-meter telescope, and the science is really cool. It's actually one of the most beautiful like images you can see, I think, in astronomy. Um, So yes, just for the audience, we want to clarify like what is a galaxy. So this is one of the very first images that we got from the James Webb Space Telescope. So this telescope is like on orbit around the sun, like in space, and is one of the best telescopes we have right now working. And it took this image of a galaxy. So you can see that the galaxy has a lot of like um, dust and gas floating around, and you can see that there's a nucleus. And in this concentration, there's a lot of stars. You can see all of these blue dots. It's just a lot of stars. And around, you see like these spirals coming out. So when galaxies first formed, they tend to have this like shape that is like a spiral. And then with time, they become more elliptical. But these are an exciting type of galaxies because you see a lot of star formation, and this star formation happens in like bubbles, and those bubbles are these red areas that you see all over the image. So you have a lot of stars, you have a lot of dust and gas, and this is how the concept of a galaxy basically. Um, so what is a gravitationally lensed galaxy? So here we have one of the best images I think we've seen of gravitational lens galaxies because it's a smiley face. Uh, so as you can see, here are different types of galaxies. Here are like a spiral, like the one we saw earlier. But there are also the elliptical galaxies that are more evolved, technically have older stars, and they're much, much older, and they look more like watermelons or, yeah, like an egg shape. And they're yellow, and and around you see like these arcs. And this is actually like an image of a galaxy that has been shaped very weirdly. And this is because of the galaxies that are in the center. These elliptical galaxies are so massive that they are basically changing the path of the light of the galaxy that is behind it. And that's why we see very, very weird shapes. And sometimes you can see, if you have one central elliptical galaxy, then if the angle is done correctly, then you can see like almost a full arch of the background galaxy around. And yeah, this is another image that is very pretty because actually you can see how this galaxy that it looks like an arc, it is technically a spiral galaxy, and you can sort of see the spiral arms in one of the multiple images. And you can see, like, for instance, this arm is very blue, so it has more blue stars, etc. So the good thing about this is that we can observe in detail this spiral galaxy because it's extended very weirdly. So we can study a lot of properties of the galaxy itself. But there's a lot more you can do with gravitational lenses. For instance, this is called an Einstein cross. So again, if the angle is set in the correct way, then you will see an image of an object behind repeated 4 times. And in this case, it looks like a perfect cross. So yes, you can study a lot of these things, and you're going to see more of these examples later on because this is specifically what it's being studied here. So the gravitational lens is this effect that was actually predicted by Einstein's theory of relativity. And we know that because of this mass, super concentrated mass in the center, in this case, the responsibles are these elliptical galaxies, these yellow galaxies in the center. They're so massive that they bend space-time. So all the objects that are behind look stretched like that. And because we're thinking about space-time, it's not just that they look like that, but also the timing of when we observe the images is different. So we're going to talk about that later, but that's just to keep in mind. And here there's like a video that is very interesting so that you can conceptualize how this happens with a glass of wine. So you can do this experiment at home. So
Oh yeah, you can definitely see how it's smeared out and
yeah,
extended.
exactly. So that's why you can do that experiment at home anytime. It's super easy. And that's the exact same effect we're seeing in space, but way more beautiful because galaxies are super amazing. And actually, we have another PhD student in our group. His name is Devon Williams. And he actually made like this simulation of how he puts like a lens that moves around, and you can see how, if you have a lens, how these galaxies start to stretch out. So there you have an Einstein ring again. And then, yeah, depending on how you move the lens, then that's how you get all these multiple images. So this is like a simulation to understand basically all the observations that we have. And yeah, so in this little panel up here, this is what we call the source plane. That is basically what it would be if there was no lens. And here is just like playing around with moving the lens around the source plane to see how all the light is bent. And there you have an Einstein cross, basically. So yeah, this is the idea of the simulation.
Oh, this is a wonderful simulation. It really makes it very
Yes.
clear how
Yeah.
the effects of the gravitational lensing.
Yes, you can absolutely like Google this on YouTube because
Okay.
it's on YouTube. So if you look for Devon Williams, who is an amazing PhD student here, you can find it.
Great. I'll add a link in the video description.
Yes, I can send it to you.
Thank you.
Yes. Yeah, one of the latest examples we saw was this Einstein cross. And this is an important like image case. So we actually have one quasar that is behind the galaxy. And the quasar is, the image of the quasar is repeated 4 times. So that's how you get the cross. And your galaxy is like here. um, yes, you can see a little bit of, because a quasar, I need to explain what a quasar is, but a quasar is a supermassive black hole that is in the center of a galaxy. So you can actually see a little bit of the galaxy structure of the quasar in the arcs. So what is a quasar? Quasar comes from the word quasi-stellar object. These objects were actually not found until the 60s through observations of something that looked very, very much like a star. And it's really, really bright. So here in this image, this is an image from the Hubble Space Telescope. We have, a lot of sources. You have stars, like all of these things that have like cross are actually stars observed from Hubble. And in the center, we have this thing that actually looks like a star. It's very bright. It has this representative shape of this cross. But as it turns out, it's not a star in our galaxy, but it's actually a super far away object. It's a quasar that is present when the universe was just like 700 million years old. And just remember that right now the universe is like 13.5 billion years old. So this is a super far away object, but it's so bright that it looks like a star. So then you start questioning, well, why is it so bright? What is making this object so bright? And the reason is that it has an active galactic nucleus. So this galaxy has a black hole in the center. So this is what we call AGN. And when you have a supermassive black hole that is like 10 to the 9 times solar masses, then this is such a powerful engine that when things start spinning and falling into a black hole, a lot of material is also ejected. Like you have jets coming out, you have a lot of particles coming out, and all of this energy, super powerful, is what we see that looks like a star. That's why it's so bright. It's just a bunch of energy that is generated by this supermassive black hole that is actively eating all the material around. So we call that like accretion, like all this active accretion. Yeah, so that is why. And quasars are very cool because they're actually one of the most bright objects you will ever find in the universe. And actually, there are other objects that are very bright, like fast radio bursts. These are other types of objects that can be brighter than quasars, but quasars tend to have a time when like a longer period of time that they're bright. So you can think of them as like standard candles in the universe. So they're always like super, super bright. When we see them, they're gonna stay that bright for our lifetime, basically, and more. So here you're going to see a simulation of the accretion of the black hole. So you understand, and it has so yeah, you have this supermassive black hole like angrily accreting, and as it's spinning and is accreting, eating everything, it like shoots out all of this energy. Yeah. sometimes it shuts out a lot of gas and dust that's falling out. So those are the layers you were seeing. And this here, this jet is just energized particles going around a magnetic field. Yeah, so those are supermassive black holes that are like monsters in the universe, and they're really, really cool. So, okay, now I'm gonna turn William to explain more about how we use quasars and gravitational waves.
Yep. So, okay, so I guess to combine the things that Sophia was talking about now, we're going to combine both quasars and gravitational lensing. So when a quasar gets lensed, we see its image multiple times. So I think in one of the previous slides here, you can see this is an example of a lensed quasar because there are 4 images of that quasar, but there's only, if you remove this lens, there's only one quasar that exists. It's just that because the light is being bent and the space-time is being bent around this lens galaxy, we actually see 4 of these of the same quasar. But the problem, I mean, one of the, oh God. One of the benefits of that is that quasars actually flicker a little bit. So over the course of days, weeks, or even months, they can flicker a little bit. And from these images, they actually flicker at different times because of how the space is being bent around the light, or around the lens galaxy. The light has to take either a longer route or a shorter route to get to us, to get to the telescope. So because of that, there's a time delay between each of these images on when they flicker, on when the quasar flickers. And we can study this value, this time delay, in order to constrain, and it helps us constrain things about the universe, such as the expansion rate of the universe or the Hubble constant. Yeah, so this is demonstrating the different paths that light will have to take for each image. And because of the different lengths of the light has to travel, we will observe a different time in which the quasar images actually flicker. Yep. So how do we measure these? How do we measure the time delays? So firstly, we could just measure the actual first we want to measure the actual time delays between the images by just monitoring them and seeing how much they flicker over time and matching the light curves across all 4 images to get the time delays for each of the images. Another way we can study the time delays for each of these images is that we can model the lens or the mass of the lens galaxy. And by modeling the mass, we can actually simulate how space and how the space-time bends the light, and we could try to replicate what we observe, the lens quasar configuration. And by doing that, it gives us the actual time delays through simulations. So there's this internal, well, okay, I don't think I'll cover this, but in the sense that we can, by studying these images, we can better constrain the actual mass and the mass profile of this lens galaxy. And by studying this mass, yeah, okay. And so one of the reason why we're observing tonight is because that we want to measure the actual kinematics of the lens galaxy. So when I say kinematics, I mean basically how much the stars are moving within that galaxy. And this allows us to this gives us a better estimate for the mass profile of the lens galaxy, and in turn helps us better predict the time delays, and hence helps us solve big questions of the universe. So it all comes back to trying to get the time delays from these imaged quasars, And by doing that, we can do that by properly modeling the mass profile of the lens galaxy. So by studying the kinematics, or how much the stars move in the lens galaxy, we can measure basically how many stars are in the lens galaxy and how it changes over its radius and how it's distributed over the lens galaxy. So we'll have some better pictures later of how that looks. But for now, let's talk more about the actual instrument itself. So what we're using is called an IFU, or integral field units spectroscopy. So what that means is that basically, if you imagine taking an image with your camera, when you take an image with your camera, it's colored. And when it's colored, it means there are different bands. There's usually a blue band, a green band, and a red band. And that's what makes it colored. Back in, the old times, we had like black and white pictures that only had one band. What IFU spectroscopy is that imagine 100 band whenever you take an image. So that's basically what this instrument that we're using tonight, the Keck KCWI instrument, is doing. It's taking a picture of the galaxy, but with 100 different bands at a bunch of different wavelengths, which allows us to study properties of how fast the stars are moving, basically, in that galaxy. So this is this is a few examples of the lens quasars that we're actually observing. So on the left-hand side are the actual images from the Hubble Space Telescope. And from this image, the second image, second to the left, second column, is what we observe from KCWI, the Keck instrument that we're using tonight. So what this actually is this is just one image, but as I was saying, IFU has basically 100 different bands, whereas the HST has just one band. So the benefit of that is that if you were to just we could basically study the velocity of each of these pixels, and here is what we call the spectra of the lens galaxy. So the spectra basically tells us what chemicals are in the lens galaxy, but at the same time, for example, this line here, these two lines indicate calcium is within that galaxy. However, when particles are moving, they tend to broaden these lines. And so we can study how much these lines actually broaden, and in turn tells us how fast the stars are moving within that lens galaxy. And this is just another example of the same phenomena. We have these calcium lines, and by studying how broad these lines are, we can estimate the speed in which the stars are moving within that galaxy, which is pretty cool. Well, I think it's pretty cool. So another thing, so this is just a map of, since basically in every pixel of this image, we can generate a spectra like this. We can generate a speed for a given pixel. We can generate a speed for every pixel, so we can map it out, and this is how it looks like. So there's this general rotation going on here. So in blue, it means that it's moving towards us. That means the galaxy is spinning towards us, and the red means it's spinning away from us. So you can imagine it's actually like a ball that's spinning, basically. So what we concluded in this map here is that this lens galaxy is spinning. And this tells us a lot more about the actual mass within the lens galaxy and how it's distributed and how we can solve the time delays. And we have a little clip on what I guess, what we're trying to solve, which is the expansion rate of the universe or the Hubble constant.
Nothing, almost.
Can you talk us through? I don't know if there is an audio, but we're not hearing the audio. Can you talk us through a bit of
Oh
what you're saying?
no.
Okay.
Oh
No
no.
worries.
Okay. Okay.
Yeah.
Maybe subtitles, but like I could okay, I guess to give a general overview, H naught or the Hubble constant is the rate at which the universe is expanding. And there are many ways we can actually measure this. For example, if we observe a galaxy that's let's say let's say 10 light years away or something, we know that the universe is expanding. If we assume that the universe is expanding, that means the space between us and that galaxy 10 light years away will grow the space between us because the space itself is expanding. If you imagine you have a balloon and you draw two dots on the balloon. If you inflate the balloon, now the dots are further apart. That's how basically it works. This is the rate at which the balloon expands is basically the Hubble constant. I don't know if that's clear enough. But
It's just trying to understand the evolution of the universe because we know it started with the Big Bang and everything was like super concentrated. And then the universe started to expand. But then we also find out that, this expansion is accelerating and everything. So we want to try to understand what is going to be the future of the universe. And for that, we need to know at which rate it is expanding, because depending on that, things can change. And that's why statistically, like when this was first measured by the astronomer Edwin Hubble, there was a measurement, but then other teams throughout multiple years tried to measure this constant multiple times. And what we find is that no one agrees because everyone is using different methods because it's really hard. And what is showing right now is that you need to determine the velocity of the galaxies that are receding from us because the universe is expanding, but also you need to know the distance very well. And to know that you need these very bright sources like quasars that are like intrinsically like by themselves very bright. So depending on the method that you use or maybe the type of galaxies you observe, everyone's getting different answers. And so we are trying to like reduce the uncertainty or like try to come up with a more reliable answer for the expansion of the rate of the universe.
yeah, I mean, like, so one of the biggest, hottest questions in astrophysics these days is what is the Hubble constant? Because a lot of like what Sophia was saying, a lot of different teams are getting a lot of different values, and no one can agree on what the expansion rate of the universe is, which is, a really important term just from the name. So yeah, that's why we're trying to do this, because we're trying to introduce a new independent method of measuring the Hubble constant, which is different from all the other well-established methods, and hopefully can, I guess, give us a better constraint on H naught, the Hubble constant.
Yes. Okay. So you're working to produce a new method of measuring the Hubble constant. Wow, that just hit me. I'm sorry. That's
Yes, it is definitely worth applauding. Yeah.
that's huge.
Yeah.
Wow. Okay. while I'm letting that settle into my brain, we do have a couple of questions,
Mhm.
and both are from Rohit. We go to the recent question and then the previous question. So the most recent question is, how is the method that you're using is that better than what DESI does?
So what DESI does, okay, yeah, that's fair. What DESI does is that it's getting the redshifts for a ton of galaxies.
Distances.
Yes, the distances. So yeah, the difference is that they're measuring redshifts or distances, whereas we're measuring velocities. So I mean, it's a minor difference, but it has huge implications. So for example, if I can click that button, oh, oh no, my exit, I don't take. Okay. For example, DESI is also getting spectra like these, but it's getting one per galaxy. What we're doing is we're getting one per pixel of the galaxy, which allows us to get much more depth within a given galaxy. So the trade-off is that DESI observes a ton of galaxies, but not as high quality. Uh, but we observe very few galaxies, but with extreme quality from Keck.
I
All right.
see, I see. And so I guess it's a matter of just being able to use as much available data as possible as you're working through trying to get to whether it's better profiles of the galaxies or getting information that you can use to create a different method for measuring the Hubble constant. I'd imagine that all of this is useful data from DESI, from CAG, JWST.
Mhm. Yep. Yep, that's right. I mean, it's always going to be trade-offs with different instruments, right? You're not going to find, well, very rarely is there like an instrument that's just objectively better than another. It's like in that's being moderately used. But so yeah, they're being used for different applications. Yes.
Excellent. And Rohit, if you have a follow-up question or comment, please post that in the chat for me. And going back to this previous question was about the method that you're using to get the mass profile of a region or a galaxy. Could you talk a bit about that?
Okay. So the main method that we use is that we model the lens configuration. So the reason why we're specifically looking at gravitationally lensed systems is because the configuration in which these are being lensed, like say these four images, tell us a lot about the actual mass of the lens galaxy. Because what's causing the lensing phenomena is that there's something extremely massive here that's causing space-time to bend. Um, and by studying how these arcs and these images are formed and are, I guess, distributed, we can very accurately constrain the mass profile of the lensing itself, of the thing that's doing the lensing.
Oh, I see. I see. Okay. Excellent. So Rohit or anyone else, but Rohit, since you shared these questions, if you have follow-up questions or comments, please post them. Otherwise, please feel free to continue.
Okay, sounds good. And thanks for the questions. Oh no, not to play that. Okay. Yeah, so uh with just only a few of these systems, we can very accurately constrain the Hubble constant. Let's see here. So with let's mainly just look at this black curve here. So with just 7 lenses, we can actually constrain the Hubble constant, which is on the x-axis here, to a very, very, very small precision. I think up to 2%, which is extremely tight and which could allow us to better constrain the expansion rate of the universe and settle a lot of the debate that is going on what is actually the value. However, there's this one obstacle in our way called the mass sheet degeneracy. And I won't get too much into detail about it, but the gist of it is that because of this degeneracy, it causes our constraints to be a lot wider. So this is the gray curve is without the degeneracy, and if we introduce the degeneracy, it becomes much wider. If we have to account for it, basically. If we account for this degeneracy, it widens our estimate of the Hubble constant by quite a bit. It becomes 9% instead of 2%, which is not as good, basically. So what we're hoping to do is that with the kinematic information, with what we're getting tonight, with the IFU data, we're able to break what's this mass sheet degeneracy, and we can turn this green curve back into this gray curve. That's the general gist of why we're getting IFU data, why we're observing tonight, basically. Yeah. So what can we do with 7 lenses and kinematics? And we hope to recover this gray curve with kinematic information of these lensing galaxies.
So you said you hope to recover that gray curve. What additional work do you have to do once you get this data to be able to start to find where that gray curve actually is within all the data that you have?
That's a great question. So what we do is that we combine our model that we get from lens modeling, which I was talking about earlier, from just modeling the image positions. We can use that model and basically tighten its constraints by measuring how fast the stars are moving, the kinematic information. And we do this by doing a dynamical model, is what we call it. And it's basically it's basically how much the stars move versus its radius. And as you travel further away from the center of the lens galaxy, center of any galaxy, the speed of which the stars are moving drops. It goes down with the distance from the center. And by measuring that gradient, we can better predict the actual mass within a certain slice of the lens galaxy, within that radius of the lens galaxy. So it gives us better constraints, more or less, and it allows us to break this mass sheet degeneracy, which I'm purposely leaving vague because it's very complex. Yeah, I hope that answered your question.
It does. It does. Thank you. Thank you. Okay, and we have another question here in the chat that also has a link. This is from Arcus. And the question is, recently the Euclid Q1 data release showed a lot of strong lensing systems. Are these methods similarly applicable over there, I assume, to what you're doing? And thank you also, Arcus, for this great link. You all can pull that up and maybe take a look at some of that Q1 data. But are these methods similar?
Sorry, I'm gonna pull up the link as well or should I pull up the link on this screen?
Sure, go ahead. Pull up the link on the screen. Or I can share it. Oh, you got it. Go ahead.
Where do I got it? Chat.
Yeah.
Chat.
Cosmos.
Yes, it's from the Cosmos. Yes, yes.
Yes.
This is
So
Euclid is different.
So Euclid is yeah, like what you're saying, Euclid is allowing us to discover so many more gravitationally lensed systems, which is amazing. The thing is specifically what we're looking at specifically are lensed quasars. So there are tons of gravitationally lensed systems, but they lack what? Oh no, what did I do?
Firefox. Okay.
How did that happen? They lack so the benefit of using a gravitationally lensed quasar is that each of these images flicker, and from that we can actually measure its time delays. With a regular galaxy, galaxies typically don't flicker in the scale of days, weeks, or months. They flicker on scales of maybe millions of years. So we're not going to be able to observe any changes within the images, unless we get really lucky with the supernova. But in any case, so these quasars allow us to actually measure the time delays. And so a lot of the systems that Euclid are discovering are gravitationally lensed systems, but they will be, and I'm guaranteeing that they will also discover a ton of gravitationally lensed quasar systems, in which then yes, that we can use these systems to newly discovered systems from Euclid to do this analysis, to do these time delay analyses.
Ah, okay, excellent. Arcus, if you have follow-up questions or comments, please post them in the chat. And so, thank you for for clarifying how each of these instruments are doing amazing work, but the slightly different focus than what you are actually looking for, which really goes to explaining how for example, the CAT Cosmic Web Imager KCWI they're using now, why it's perfect for what you are trying to achieve.
Yep. I mean, this instrument is also like the state of the art for IFU spectroscopy. So we're very fortunate to have time to observe with it as well.
Yes, excellent, excellent. And so, while we're waiting for any more questions or comments, please continue because I see that I think you have a few more. You have a few more slides, and then I thought maybe we could, for those who joined after we talked about the weather, take another look in this last 10 minutes at the weather and see if you think things may start to clear up for you.
Okay, sounds good. I think I only have one more slide. It's basically just a conclusion. Oh no. Oh, okay, that's fine. Basically, that's the conclusion. It's just to conclude, we're using these lensing galaxies, lens quasar galaxies, and we're studying their kinematics with the Keck KCWI instrument in order to break these degeneracies that lie in our that helps. Well, okay, it allows us to break these degeneracies that lie in the way of us being able to constrain H naught to such a high precision. Oh God, that was a word salad right there. But
It
yeah.
was. Could you maybe break that down for us again, though?
Yes. Yes. So we're using these lens quasars to be able to constrain the Hubble constant to a very tight constraint, to be able to settle a lot of debate on what actually the Hubble the Hubble constant value is. And we're using the kinematics from these lens galaxies using the Keck instrument that we're using tonight. We're using these kinematics to better constrain the lens galaxy mass profiles, and in turn allows us to better constrain the Hubble constant as well. So that's the general gist of it. We're using lens quasars to fit for the Hubble constant, the expansion rate of the universe. That's the gist of it. Yeah. So
And I think if I can jump in, I think something important to note with this graph is that in the green, this horizontal bar is like the uncertainty, so it may go from, I don't know, 68 to 79, which is a large range. So this green bar is using 7 lenses, but without doing the kinematics properly. But if you look at the red, that's using just 1 lens with proper kinematic estimates of the stars, and the uncertainty is not that different. So the hope is that once we finish observing like 7 gravitationally lensed quasars, and we they do all these proper MSD, or they account for these kinematics, that's already promising to improve the result and truly get to the 2% precision that we can get, for instance, to recover this gray dot. So that's why we get many multiple nights with Keck to observe as much as we can these 7 gravitationally lensed quasars.
Yes. So hopefully we can join you in an upcoming session where the weather is a bit more favorable. Uh, Before we move to another question, I'm sorry, before we look at the weather on the summit, we have another question from Rohit in the chat there. When you use the Keck Cosmic Web Imager, KCWI, do you have to account for the velocity dispersion within the galaxy in different pixels? And does that affect your overall measurements?
Yeah, that's a great question. So we're actually, yeah, so the succinct answer is yes. We are looking at every pixel within the KCWI data. And we're getting a velocity dispersion, or this is mapping the velocity, but we're also mapping the velocity dispersion for every pixel. Let's see. This is this is velocity.
From your data, in your computer, maybe?
I may have to pull it, but in any case, yeah. So in every pixel, we do have information for the velocity and velocity dispersion. So typically, when you look at a spectra for a given galaxy, they average out all the pixels, or they average out the entire a large aperture of the lens galaxy to get you a velocity dispersion. The benefit of this is that we now have resolution for a given location of the lens galaxy. So let's say in this part of the lens galaxy, what is its velocity dispersion? In this part, what is its velocity dispersion? And this allows us to get a better picture of the actual mass profile of the lens and the mass. Yeah, I hope that answered your question. Yeah.
Yeah, so Rohit, please, if you have follow-up questions or comments, drop them in the chat. But as you were saying, William, that in some cases they actually would average out that dispersion so you don't get this kind of granular detail that we can see right here for each of the pixels. What is the benefit? There seems to be there has to be some benefit to both methods. Why would some average out that information versus having it be more distinct, like you have it?
Yeah. For one thing, you need an IFU instrument, integral field unit instrument, in order to be able to do this pixel by pixel analysis. Whereas a lot of spectroscopy instruments don't do that. They basically just use a giant aperture, very usually, yeah, just a large circle basically to look at the overall velocity dispersion of a galaxy. So that's what makes IFU spectroscopy much more powerful, because it allows us to get better, because it tells us a better story. Like in terms of this galaxy, we know that this galaxy is rotating now. In a typical slit spectroscopy unit, where we wouldn't have these pixel by pixel values, we would just get one velocity dispersion. We wouldn't be able to tell it that it was rotating. But because we have all this extra information, it tells us much more about these lens galaxies.
Excellent. And so let me see. I think I have another question. Um, First, we have the founder of Shadow the Scientist is joining us, Raja Guhathakurta, in the chat there. And Raja is on the way to the airport. So let me make him co-host here. Raja's on the way to the airport. So first, the question was that Raja posted, and everything comes to me first. Yes, so they are talking about um, galaxies that are gravitationally lensing objects, of course, in the background. And then here is another question here, or Raja, I'm going to post it for everyone, but Raja, I don't know if you're driving or not, but if you'd
No,
like.
I'm not. I can speak.
Oh, okay. Yes. Excellent. So I'm dropping the rest of Raja's question there in the chat, William and Sophia. But Raja, yeah, please expound on that question.
I guess, Sophia, hi there. It's been a while. How are you doing?
Good, how are you?
Good, good. Thanks for doing this. And William, we haven't met before, but I guess my first question was, you mentioned lensed galaxy. Do you mean lensing galaxy? The one you're measuring kinematics for?
Yes. Yeah, I apologize. Yeah.
No, that's okay. That's okay. Just want to make sure.
Yep. So yeah, I should have made the distinction much more clear. So lensing galaxy typically refers to the galaxy that's doing the lensing. Lensed galaxy would refer to the actual source galaxy, the background. Yes. I should have made that clear. Sorry about that.
No, that's fine. That's fine. And I was just wondering, my other question was, this is follow up to Rohit's question about, is there dispersion within each pixel? Something that I've seen people do before is take the quadrature sum of the rotation speed of the galaxy and the dispersion, so that if, some of that dispersion in a pixel is real dispersion, some of it is velocity gradient that's manifesting as a dispersion. But when you take the quadrature sum, you get everything, all of the gravitational effects or the kinematical effects of the galaxy manifested. Right? Is that a standard technique to take the quadrature sum of the rotation and dispersion?
It is. Because I guess what we're actually trying to constrain in the dynamical model is the Jeans equation, where we're trying to measure how much energy is within a given patch of the galaxy. So yeah, in order to do that, we actually get the quadrature sum of both the rotation and the rotational velocity and the dispersion as well.
Got it. Got it. Thank you. Thank you very much. I love this. I love gravitational lensing. And is it okay if I ask one more question, please? And I promise I'll keep quiet.
Yeah, go ahead, Roger. We're just about to wrap up. Perfect.
Okay. So do you measure a time delay between the two quasar images? Is that the basis of this Hubble constant measurement?
Yes. So we have a monitoring program to measure the light curves for every image, and we're also modeling the mass profile and trying to predict the lens images. And by comparing the two measurements, we can fit for the Hubble constant.
Right. Because the time delay gives you a time scale, and normally you have an angular. I mean, you have a distance difference, a path length difference, but until you know the exact mass model, you can't pin down the path difference exactly. So once you get a path difference and a time difference, you know the speed of light, that gives you a Hubble constant.
Yep, exactly. And I did neglect a little bit a small part in the presentation, but it's not just the path length that's being changed by the lens galaxy, but it's also the Lens Galaxy is introducing a what's called a Shapiro time delay, in the sense that when light is in the presence of more gravity, it slows down. Is the general concept. So there's the difference in path length and the Shapiro time delay.
Got it.
Mhm.
Thank you so much. And Jamaica, thanks for doing this in the middle of the night for you.
Yeah, no worries. I'm glad you could join us. Safe travels.
Thank you.
Okay, so at the very beginning of this session, we took a look at the summit of Mauna Kea because you shared with us that the dome is closed and you aren't able to be on sky at the moment. So I'm going to share my screen just to take another look at the summit as we wrap up. And anyone in the chat, if you have more questions, please feel free to post those now in questions or comments for Sophia and William. And let me just share my screen here. Okay, so a bit of change. We can now actually see that that white blob that was ghostly actually is one of the two domes of Keck telescope, and we can see, and which is on the western ridge, and we can see across on the eastern ridge, CFHT and Gemini there. The fog seems to be dispersing. What does this mean for you all, Sophia and William?
So
Maybe we could observe. Maybe.
so the thing is that the also like yeah, the fog has to disperse, but also we need to check that the humidity goes down. And what we're seeing in our, because we have like in our monitor we can see the weather basically and this percentage of humidity, and it's still pretty bad. So even after you reach the good level, like an okay level to observe, you have to wait like 20 minutes, is
Yeah.
it? So that you know it's stable, and then you can open the dome. And we finish observing in an hour, like then there's sunlight, coming. So yeah, I think unfortunately today we didn't get any quasar data.
We had
Yeah,
20 or 20 minutes worth. Yeah,
something.
we got something, but it's not ideal. Far from ideal.
Yeah.
Yes, yes, and I know the constraints for opening, or it's different for different observatories. And for Gemini, once the relative humidity is below whatever the threshold is, then they have to wait 45 minutes for it to has to be at that level for 45 minutes before they'll even considering opening. I think it's about 45 minutes, but I know it's more than 20 minutes. But the capabilities, those thresholds are different for the different observatories, and the locations in the summit area is different too, and they experience that humidity in a different way sometimes, which is pretty crazy to think about. So hopefully you'll get maybe a bit more observing in. But if you don't this evening, when is the next time we could possibly join you?
So we will be having another observation night Wednesday. Wednesday, yes. So I guess 2 days from now, I will be observing. So I will, yeah, it will be around the same time. Yeah.
I see, I see.
But William will.
Okay, all right. Well, either way, we're certainly looking forward to while you see a bright light over here behind the
Yeah.
Keck Dome. Someone must be walking outside. Um,
The fog.
yes, in the fog, which you can. I wonder if they're checking for ice or
Maybe, yeah.
something
Yeah.
ice buildup before opening. So I see it's negative, like -2, something like that. I was looking at Brian's earlier weather. What's the current temperature there at the summit?
Negative 2.8.
Yeah, yeah.
-2.8, right. Yeah. So maybe they're looking for any ice buildup.